The intake manifold pressure sensor is a transducer that generates an input signal to the ECM proportional to the air-fuel mixture pressure in the intake manifold. The ECM uses this signal to adjust the base timing and as an input for air mass calculation. Remember, the manifold pressure after the throttle plate may be different from the turbocharger boost pressure. The engine position sensor measures the position of the engine camshaft by the use of a variable reluctance sensor and 7 cast protrusions located on the rear of the camshaft gear. Whenever the cam gear protrusions pass the engine position sensor, the deflection in the sensor flux lines generates an alternating current signal to the ECM. 6 of the 7 cast protrusions on the cam gear are located 47 crankshaft angle degrees before top dead center, 1 protrusion for each of the 6 cylinders. The engine position sensor sends a signal to the ECM based on these protrusions passing the end of the sensor. The ECM determines proper ignition timing and engine speed based on these signals. The 7th protrusion on the cam gear is located 30 crankshaft angle degrees after cylinder number 4, the last cylinder in the firing order, or 90 crank angle degrees before the protrusion for cylinder number 1. Because of its location on the gear, the signal from the 7th protrusion breaks the consistent time interval of the signal from the other 6 protrusions. The ECM interprets this 7th signal input as the beginning of a new cycle in the firing order and generates a timing reference signal for the ICM. The ECM uses the frequency of the signal resulting from the 6 evenly spaced cast protrusions passing the engine position sensor to calculate engine speed and, with the intake manifold pressure sensor input, adjust the ignition timing. The ECM recognizes the 7th signal from the 1 unevenly spaced protrusion as the indicator for the start of a new cycle. Each cycle begins with cylinder number 1 as the next cylinder to fire. The ECM uses this signal to generate the spark reference signal for the ICM. The spark timing signal to the ICM defines the ignition timing for each cylinder. The timing signal is defined by the intake manifold pressure sensor and the engine position sensor inputs. The ECM uses these signals to make timing adjustments and sends a spark timing signal to the ICM. Using the ECM to control engine timing eliminates the need to check or adjust engine timing. The spark reference signal from the ECM to the ICM indicates to the ICM that cylinder number 1 is next in the firing order. The ECM receives the input from this signal from the engine position sensor and the 7th protrusion on the camshaft gear. There is 1 spark reference signal for each 6 spark timing signals. The ICM sends out ignition signals to achieve the correct firing order of 153624. After receiving a spark reference signal from the ECM, the ICM fires the spark plug for cylinder number 1, then the next spark plug in the correct firing order each time it receives a spark timing signal. After firing all 6 plugs, the ECM sends another spark reference signal to start the sequence over. Although engine timing is controlled by the ECM, not the ICM keeps track of the firing order and fires each plug in the correct sequence. The ICM contains a DC to DC converter and a separate coil driver for each spark plug. The DC to DC converter steps up the 12-volt battery supply voltage to 300 volts. This voltage charges the capacitor in each of the coil drivers. The spark timing signal received from the ECM causes the ICM to close the trigger switch, sending current flow from the ICM capacitor to the coil pack or the coil-on plug assemblies, COP. The ICM has a built-in engine diagnostic capability. The ICM monitors the primary ignition circuit for continuity on the coils for cylinders 3 and 4. If continuity is not present, the system will not open the fuel valves and the engine will not start. Therefore, disconnecting the harness from either of these two cylinders shuts down the engine. When the piston reaches the correct position in the compression stroke, the ICM closes the switch to the ignition coil. The current flow in the primary windings induces a high voltage into the secondary windings. This high voltage is delivered to the spark plug by the spark plug wire. The resulting voltage creates a potential difference between the center electrode and the ground strap. The voltage continues to build until it is great enough to cause current flow across the air gap between the electrodes. The center electrode is negative with respect to the ground strap. Therefore, the electrons flow from the center electrode down to the ground strap. The current flow creates a heat path of approximately 30,000 degrees Fahrenheit, igniting the air-fuel mixture. The plug continues to arc until the energy in the secondary winding is dissipated below the breakdown voltage, or until the switch is opened, removing the capacitor from the circuit. This allows the capacitor to charge for the next cycle. Spark plug life is largely dependent on the cleanliness of the porcelain insulator. Dirt, oil, and fingerprints reduce the seal strength between the spark plug boot and the porcelain, causing reduced plug life. Do not touch the porcelain insulator of the spark plug. Use rubbing alcohol and a lint-free cloth to clean the spark plug porcelain and magnetic spark plug socket before installing the spark plugs.